We'll hit current slide and go from here. Now, one more announcement. You've heard the others. Always looking for math team members. It's a lot of fun. You learn a lot of math. Great opportunity. They meet tomorrow at noon, and every Friday, except next Friday, of course, at noon. And in Birmingham West Campus, the C building, which is Science Building, C100. And if you're coming from the library building into the C building, first room on the left, okay, is C100. They also meet Monday evenings, but not next Monday, at 3 o'clock in the afternoon. And the guy in my class, Mondays and Wednesdays, said they really had a lot of fun, and I can tell a huge difference. At the first of the term, he was very hesitant, not certain, and now he's popping up with the answers right off the top. So he's learning some math, really, and in a fun way. Now, here's something else, and I learned some more stuff about it this morning from a student in my other class. They sent these flyers around. These are informational sessions. You'll probably see them posted around the thing, about two issues: institutional scholarships and summer Pell. Okay? And I started the announcement with summer Pell. Sometimes you may have money left over, and if you do, you can use it in the summertime. And one of the students sat right back there in the corner said, actually, they changed the law this year, and if you get your FAFSA done now, you can use that in the summer for next year. Next year's Pell, you can use starting in the summertime. So they did this, I'm guessing about 7 or 8 years ago, and it was a resounding success. I mean, we had just record numbers of summer students there because they had money to come, and just enrollment just really went high. It was fantastic. And then after a year or two of doing that, Congress decided they didn't want to spend that much money, so they cut back. So, but now they're evidently trying it again. So it sounds good to me. Or someone snuck a way around it. I don't know how. But anyway, the other issue is in institutional scholarships. Now, it used to be if your Pell money had run out, you could apply for one of those summer scholarships. Okay? You still can, but if you get your Pell in time, you can use your Pell. But this is for students who may not qualify for Pell. There's institutional scholarship money available, and there probably will be more available this summer because a lot of students will be taking advantage of the Pell. So there is money set aside, both institutional scholarships and summer Pell. The informational sessions will be Wednesday of the week after next, because unfortunately you know what next week is. Spring break, we won't be meeting. Sorry about that, get over it. So not next week, but the Wednesday after we come back, April the 4th, 2 sessions. One from Wednesday 11 to 1, and the second one 5 to 6:30, both on Wednesday. On the Bassmer campus, this is in the faculty staff dining room. And here is the map of how to get there. You go out of the door here, down this long hallway here. Don't go down the first stairwell, go down the second stairwell. Just go that first half light down, and then go and wander around a little bit here going toward the cafeteria. The cafeteria is right here. The faculty staff dining room is right there on that hallway. Nursing classroom. Actually, it's now a student lounge type area. One of these rooms, I think this one. And then the faculty staff dining room is right across from that. Okay. And I don't know if y'all knew about the student lounge, but fairly comfortable seating in there, and it's a good place to hang out if you're needing to spend some time between classes and can't find a room to do that in. Okay, so both of those meetings, faculty, staff, dining room. Now, if you happen to be on the Birmingham campus on Wednesday, you can go to that one that's in the Leon Kennedy Center, and that's actually in the cafeteria. That's going to be interesting because 11 to 1 is when they serve lunch, okay? And maybe even 5 to 6:30 they serve for their resident hall students. So I don't know how they're going to do that because it says it's in the cafeteria. But both meetings are sponsored, all 4 meetings, sponsored by the Office of Student Financial Services. So take advantage of that, find out about it, go for it. Okay. Now, any questions on anything before we get started? All right. Now, where we left off last time was example 10 and then 11 in section 5.3. But neither one of these were in the PowerPoints for 5.3, so we said we'd start in 5.4, so that's where I'm going to be. So we're not going to do this yet, but I'm going to do the example on this slide. Okay? It says find all solutions for this. Whoops, let me get my pen activated here. Sine squared x minus 3 sine x minus 2 is equal to 0. My pen is doing really weirdly today. In the interval 0 to 2 pi. Counting 0 but not counting 2 pi. All right. What would be your approach for finding all solutions for that trigonometric equation on the interval? Yes, you cannot factor that. The only possible factorization would be sine minus 2 times sine plus 1, and that doesn't add up to minus 3. Okay, so yep, factoring's out of the question. So what do we do? Quadratic formula, exactly. And how does that go? Anyone remember? Okay, yeah, but what is equal to that stuff? It used to be x, or whatever your variable was. Now it's sine x, because you're treating that function like your variable. That's the thing you're squaring in linear and stuff like this. So sine x is equal to minus b, go on, plus or minus the square root of b squared minus 4ac, all divided by 2a. Perfect. Except what's your a, b, and c? What's your a? It's what? 1, the coefficient of the quadratic term. What's your b? -3. And what's the c? -2. Okay, so now it's plug and chug time. Okay, so it'll be, what is minus b? It's the negative of the -3, which is 3. Positive 3 plus or minus the square root of, and what's b squared? 9, because it's -3 squared, minus 4 times 1 times -2. Okay, all over 2. Okay, 2 times 1 is 2. Okay, now what I like to do next, this is just my preference, is 3 plus or minus the square root of 9. Next thing I like to do is count minus signs. Okay? What did that? Oh, I bet you I do know what did it. My chair probably pulled on the cord here. It keeps doing that. Such a pain in the neck. Okay. Here we have 3 numbers. This is always a -4. So count the number of minus signs. Counting this one. 1, 2. 2 minuses make a plus. Okay, so that becomes a plus down here. And then you multiply the numbers.
And that would be 4 times 2, 8. Okay? All divided by 2. So this would simply be 3, if I could write, plus or minus the square root of a nice round number, 17 over 2. So that actually gives us 2 solutions. Either sine x is equal to 3 plus root 17. Please tell me I've done this right. Yep, it is, okay. Over 2, or sine x is equal to 3 minus root 17 over 2.
Now, I'm most interested in finding out what 3 plus root 17 over 2 is. Now, I'm going to make a guess to begin with. Is that okay? This is a little bit more than 4, right? Okay, 4 plus 3 is 7, so it's a little bit more than 7. Divided by 2 would be 3.5. A little bit more than that, in fact. Can sine x ever be 3.5? No, it can't be outside plus or minus 1. So this one is history, folks,
not a solution. Okay, I don't know why my pen isn't writing. Okay, now,
let's see if we have any hope here. This is going to be a little bit more negative than 4. So that's like a minus 4 and a little bit more. 3 minus 4 is a little bit less than minus 1. Minus 1 over 2 is a little bit on the negative side of negative 1/2. Ha! Sine can be that. Okay? So I wouldn't even mess with this one. You know it can't work. So best you can do is, this isn't one of our favorite little values, is it? No. So we're going to have to do an inverse sine, right? So that makes the x equal to inverse sine or arc sine of this thing. 3 minus root 17 over 2. And if you've got a calculator, which I hope most of you do, you can plug that in, 3 minus root 17 divided by 2, get your answer, take the inverse sine of that, see what your x is. I can guarantee you it will be a negative number, because that's a negative number, and sine is only defined in that little range. So it's going to be a slight negative number, and I would say in radians it's probably going to be about negative 0.5 something. I don't know. I'll let you do it and see what you get. Yeah, negative, almost negative 0.6 something. It's negative point. You get an answer yet? Get one? Oh, okay. What do you get? What's that? Okay. In the book, they got negative 0.5963. Okay? And what's the problem with that, folks? It's not on my book. Uh-oh, spaghetti-o. But, remember, sine is a periodic function, so we can add what to that? 2 pi to that. So, whatever that number is, add 2 pi, which is what, 4, 7, 6, 4, 2, 8, whatever it is, and see what you get there. It's going to be about 6 point, no,
add a negative number to that. So 6.28 blah, blah, blah. If you're subtracting this from it, it's 5.6 something another. What do you get? Okay. So say it a little bit louder. All right. Wow. Okay. So there's one value of x for which that's true. Here I've done it again. Okay. Now, that may not be the only one. Okay. And here, I did it. Yanked my computer almost off the table. Okay. Now, what I'm going to do here is draw a sine function. I do this in the book. If you like theirs better than mine, you can go for it. Sine starts at 0, goes to plus 1 at pi halves. It goes to 0 again at pi. It goes to negative 1 at 3 halves pi. And goes back up to 0 at 2 pi. Okay, except we're not quite going to 2 pi. We're starting here. Now this one we just did, remember we were down here at x equal negative 0.6 approximately. So if this was negative pi halves, that would be about 3.5, a little bit more negative than that. So 0.6 would be somewhere about here. Okay, so in other words, you're down here for your y value. Goodness gracious, this is such a pain in the neck. Okay, and what we did, we added 2 pi to that. We got this point over here, just as it was coming up to reach 2 pi. But you see, we skipped right over 1 here. Okay, there was another 0 in there. Okay, and this is between 0 and 2 pi. So how do we get this one? Well, the same difference this one is from 2 pi, which was 0.5963. This one is added to pi. So this time take this number, but not the negative, but the positive, and add it to pi and see what you get. So pi is 3.1416, right? And add to that, not the negative, but the positive, 5963. Okay? And that's going to be 3.7379 or something like that. Okay, so there's another value. So we have, there's one, and there's one. Okay, let's see what they got in the book. 3.7379 and 5. They got 6869. Would you agree with that? 6869. That's what they said anyway. And since we got the right answer there, I'm guessing that's the correct answer. So 2 values between 0 and 2 pi. The one we came up with was not, okay, first, this one couldn't even be a sine because it's greater than 1, or less than, no, greater than 1, okay? This one did give us an answer, but it was outside our domain. So the first thing we did was add 2 pi to that and get it inside the domain, so that gave us that value. But then just looking at the graph of this, you see we missed one here. So if we have this difference here, that difference right here, added to pi, that would give us a certain value. So to me, the graphs help a lot. They show you those relationships that you need there. Okay. Any questions on that? All right. Let me clear all these out if there are no questions, and we'll do example 11. This is a lot of examples in this section. Okay? The surface area of a honeycomb cell The surface area S in square inches of a honeycomb cell is given by S is equal to 6HS plus 1.5 S squared times square root of 3 minus cosine theta divided by sine theta. I should have had you derive this formula. What am I thinking? Okay. Now, this is good for thetas in between 0 degrees and 90 degrees. And it will let you equal 90 degrees. You can't be 0, but it can equal 90. I doubt if it will, but theoretically it could. Okay, where h is equal to 2.4 inches, okay, and s is equal to 0.75 inch. Okay. And theta is the angle shown in the figure at the right. I'm not about to draw that figure. So if you don't have a book, look on with somebody. I can't possibly draw a three-dimensional honeycomb cell there. But it's basically the angle between the apex of the cell and the slant that comes off the apex and the vertical dropping from the apex. That's your theta. It says what value of theta gives the minimum surface area. Okay? So if you're looking for a minimum surface area, now remember your H's and S's are fixed. For this cell, they're fixed. So it might not be a bad idea to go on and plug those values in. So let's do it. S is equal to 6 times 2.4 times 0.75. Can someone give me a number for that? 6 times 2.4 times 0.75. Well, 0.75 of 6, 3/4 of 6 would be, it's still messy. So just plug it in. 6 times 2.4 times 0.75. Say again? 7.8? Is that what you said? Huh? 6.8. 10.8. Okay, that sounds better. 10.8, and that will be square inches. Okay, not that you need those here. Plus 1.5. I'm not going to write that. I want you to do 0.75 squared times 1.5. It's going to be a small number. Second? 1.5 times 0.75 squared. So do the 0.7. Second? 0.84. 3. Okay, we'll stop there. And we'll do those in square inches. Times the square root of 3 minus cosine theta over sine theta. And we want to minimize that surface area. All right. Now, obviously, you can't, I don't know if this is obvious or not. This is a fixed number, right? If you could make that equal to 0, then that would be, that would be a small value. Anything greater than 0 there, you're adding something to it. So what we really want to do is make that the most negative as possible, right? And how do you make that the most negative as possible?
I keep wanting to take a derivative, but this is a calculus class, so let's not take a derivative, okay? Oh, you know how they do it? In degree mode, they do it on a graphing calculator. So I was racking my brain to try to come up with a, short of calculus, a way to do this. So they did it on a graphing calculator. Not very fair, but if you got a graphing calculator, plug it in, plug it in. You can keep your H's and S squares and stuff to the most digits you want, do that, and graph that S and see where it comes to the minimum value. Okay? Your graphic calculator will find that for you. If you don't know how to do that, get with me and I'll try to help you, because all different graphing calculators, not all, but most of them have their own very special little syntax, and I have to do some head scratching and looking at it. But they come up with a minimum value of 11.99 or almost 12. Okay? And that occurs when your theta is 54.7356. And that's your x value. So, we're not going to do that. Okay? If you got a graphing calculator, knock yourself out. And there's a checkpoint there. You can check that as well. Okay? And it says remark using calculus, which is what I was real tempted to do, but since y'all haven't had calculus, I couldn't do it. Okay, let's do vocabulary, unless y'all are still busy on that, in 5.3. When solving a trigonometric equation, the preliminary goal is to blank the trigonometric function on one side of the equation. What are you going to do to that trig function on one side of the equation? We're going to shun it. No, we're going to isolate it. No, okay, yeah, okay. Get it by itself. So isolate, I think, is the word they're looking for. Isolate the trigonometric function on one side. And then you'll know what the function is. Then you can work on what the argument of the function is. Number 2. The blank solution of the equation 2 sine theta plus 1 is equal to 0 is theta is equal to 7/6 plus 2n pi, and theta is equal to 11 pi 6 plus 2n pi. I may have left off saying my pi in the first one. What do we call that solution, where n is any integer? Very high-ranking person in the Army. Oh, not military people, huh? Or Air Force. Not in the Navy. Yeah, I do too. General solution. High-ranking generals, they run the Army, right? Okay. The general solution of the equation. This is just a picky little word. Number 3. Let's see, we're doing real well on these, aren't we? The equation 2 tangent squared x minus 3 tangent x plus 1 equals 0 is a trigonometric equation of the blank type. Hint here is, what's the maximum exponent of your trig function? Two tangent squared x minus 3 tangent x plus 1 equals 0. Maximum exponent of the tangent function. 2 tangent squared x, 2, okay? So what do we call an equation that the maximum exponent is 2? Oh yeah, that was pre-calculus algebra. We can forget that, can't we? I hope not. What do we call them? It sounds like it has to do with 4, but really it has to do with 3. Quadratic. It's a quadratic function, a trigonometric equation of the quadratic type. Cubic would be the maximum exponent 3. So quadratic is maximum exponent 2. All right, number 4 is going to be the only chance we have left.
A solution of the equation that does not satisfy the original equation is an blank solution. Oh boy. This is the one we ran into when we squared both sides. I said you always have to check them because you might wind up with an, say again? Yeah. That's where we had to square the equation. Yeah. Example 6. Yeah. Oh, it's in the, yes. It's in the little statement right at the bottom of the page. They don't even bold it anywhere in here. I was looking for a bold. But it says, of the 3 possible solutions, extraneous, that's it. Okay. Tough vocabulary there, Okay. Homework exercises, any of the odds 5 through 9. They're all at calcchat.com. None of them are at CalcView. Any of the odds 11 through 27, they're all at CalcChat. 13's at CalcView. Any of the odds 29 to 37, they're all at CalcChat. 29's at CalcView. Any of the odds 39 to 45, they're all at CalcChat. 39's at CalcView. Do number 47, it's the only one like that. Pretty alpha graph. Pretty simple, I think, but it's also at CalcChat. Do any of the odds 49 through 57. They're all at CalcChat, none of them are at CalcView, but it says you use a graphing utility to approximate. So if you don't have a graphing utility, I guess you can't do it, but if you do, try it. All right, then we have any of the odds 59 through 69. They're all at CalcChat. 61's at CalcView. Yes, sir. I'm sorry? Okay. Can you see me at 10:45? Okay. All right, because I'm in the middle of class right now. All right. Okay, where was it? We had done through 69. Do either 71 or 73. They're both at CalcChat. 73's at CalcView. Do either 75 or 77. They're both at CalcChat. Neither at CalcView. Do any of the odds, and again, this is approximating maximum and minimum. You're probably going to need a graphing utility for this. Any of the odds 79 to 83. They're all at CalcChat, none of them are at CalcView. And then do 85 is at CalcChat, not at CalcView. And try number 87 is at CalcChat, not at CalcView. Try 89 is at CalcChat, not at CalcView. And then there's some, well, I guess starting with 87. I'd say do any of the odds 87 through 95. And they're all at CalcChat, none of them are at CalcView. Then do number 97, that's at CalcChat, but not at CalcView. And then you can look at the true-false 99, I think it's at CalcChat. Then there's a couple, there's a Think About It 101 that you can look at and see, and a graphical reasoning on 103. You decide whether you want to do those or not. All right, now we're ready for Chapter 5, Continual Analytic Tree. Any questions on 5.3? Okay. 5.4 then is sum and difference formulas. Got a few more formulas to do. And you can consider these as identities as well. Okay, because they're not just a formula, they're also an identity. So the objective here is to use the sum and difference formulas to evaluate trigonometric functions, verify identities, and solve trigonometric equations. Same thing we've done before. We're just going to add a few more to our tool belt. So we'll use the sum and difference formulas.
Now, this starts out with just some new, basically identity formulas. Okay, these are always true. It's just they're a little more involved. And once you sort of get the hang of them, they're not hard to remember. Okay? So here's the first one. If you're trying to take a sine of the sum of two angles, okay? Well, if you have the two angles, just add them together and take the sine, right? But if you don't know the angles, but you know they are there, then the sine of the sum of two angles is the sine of the first times the cosine of the second plus, same sign here, cosine of the first times the sine of the second. Now, in one text I've taught from, they actually gave a geometric proof of this. It took a while, okay? It was pretty involved, but you can see why that's always true. I don't want to go back and do that. Time is an issue, and also it's just pretty complicated. And if I don't remember exactly all the steps, you probably wouldn't either, so it's not worth it, I don't think. All right, but if you can remember this sine of u plus v, sine u cosine v plus cosine u sine, you can remember that. You don't have to learn the second, okay? Because the second is the difference between two angles, okay? Sine of u minus v. Well, all you do here is everywhere you saw a v up here, put a minus v in its place. So that'd be sine u, that's the same, times the cosine of minus v. Well, what's the cosine of minus v? Yes, it's cosine v. So that doesn't change. So that first term doesn't change at all. Then it's plus the cosine of u, that doesn't change because you didn't do, times the sine of v. What's the sine of minus v? Negative the sine. So that's why the minus sign comes here, because it's negative sine v. So you see this is identical. It's just that because sine of negative v is minus sine v plus minus. Okay? So just knowing what you knew before, if you know the first one, you got the second. So here's another one you'll need to know. Cosine of u plus v. All right? And again, there is a proof for this, geometric proof, and it's hairy. Okay, so we really don't want to go there, but just take their word for it. It's cosine u, cosine v, minus the opposite sign here, sine u, sine v. Okay? So if you just remember that for sine of the plus, u plus v, it's sine u cosine v plus cosine u sine v. You got both functions in there. And you with a plus sign in between. So the signs are the same. When you go to cosine, though, the sign is the opposite. U plus v would be cosine u. Cosine v, start with both cosines minus sine u sine v. Then for cosine u minus v, do the same thing we did before. Everywhere you saw a v here, put minus v in its place. Cosine of minus v is cosine v. So that stays the same. But sine of minus v is minus sine v, so that changes this minus to a plus. Okay? So cosine of u minus v is cosine u, cosine v plus sine u sine. So if you just remember one of these, say the sum formula, you can always come up with the difference. Okay? Really easy to do. Now, the tangent of u plus v is not nearly so simple. Okay? But it's pretty straightforward. It's not anything really super complicated. And here's how I try to remember it. You know what I do? I don't even try to memorize these things. I look them up. If you ever need it, look it up. Because guess what? If you were working for me and this was a big project we were on, I don't want, oh, I think I remember that. No, I don't want you to think you remember it. I want you to look it up and make sure it's that, okay? So in real life, I always suggest you look things up. Don't try to base on memory. See, I have a really poor memory, okay? So I don't ever base anything on my memory. It's just I've learned not to. Now, I do tell people sometimes I have a really good memory, it's just short. Okay? So tan u plus v is tan u plus tan v divided by 1 minus, the opposite sign here, tan u times tan v. Okay? And if you do get this one down, then all you have to do is change over here v to minus v. Well, tangent of minus v is negative times tangent v. So that changes that sign to minus. The u stays the same because you didn't change the u. So it changes the sign of tan v. And then in the denominator, 1 minus tan u would be the same, except tan v and tan of minus v minus tan v, so that changes that sign as well. So once you have one, you got them both. You just change the sign, you change both signs. So example 1 shows how the sum and difference formulas can enable you to find exact values of trigonometric functions involving sums and differences of our special angles. We've been away from our special angles for a little while. So nice to be back to them, isn't it? So let's do example 1. Find the exact value of sine of pi 12ths. That's not one of our special angles. But it's a combination of a couple of our special angles. So what I like to do here is write down what are our special angles. Y'all remember what they are? Special angles. Okay. 0 would be 1, but 0 is not going to be much fun. So it's going to be pi 6, pi 4ths, pi 3rds, and pi halves. Those are our special angles. We know that. And 0 is too. We like 0, but that's not going to add or subtract much. Well, we want something in 12ths. So what I want to do is rewrite those angles in terms of 12ths. How many 12ths is pi 6? 2 pi 12ths, right? How many is pi 4ths? 3 pi 12ths. How many is pi 3rds? 4 pi 12ths. And how many is pi halves? 6 pi 12ths. And of course 0 would be 0 pi 12. So that's not going to give us much. So how can we get a pi 12ths out of a combination of two of those? A sum or a difference? Either 3 minus 2 or 4 minus 3. Either one. Which you want to use? Huh? 3 minus 2. So we're going to do pi 4ths minus pi 6, right? So pi 12ths we know has to be the same as sine of pi 4ths minus pi 6, right? Now what did our difference formula just tell us? This is equal to sine of the first, which is pi 4ths, times the, for sine it was sine and cosine. Cosine pi 6, and what's SIGN sign do we use? Minus, same as you use up there, minus, and what goes after it? Cosine pi 4ths sine of pi 6.
So that's going to be exactly that. Well, because these were our special angles, we know what they are. What's sine of pi fourths? Don't we? Sure we do. Sine of pi fourths. Okay. I like to go back and draw my little first thing here. The sine of 0 is the square root of 0 over 2, which is 0. Pi 6 is the square root of 1 over 2, which is 1/2. Pi fourths is square root of 2 over 2. There it is. And pi thirds is the square root of 3 over 2. And pi halves is the square root of 4 over 2, which square root of 4 is 2, 2 over 2 is 1. Okay? That's how I remember these easily. So sine of pi fourths is square root of 2 over 2. Why is the pen so stinking slow today? Okay. Now, what is cosine of pi sixths? Okay. What did you say? You may have said it right. I don't think so. Cosine, see, that was sine. Cosine starts up here and goes this way. So that would be square root of 3 over 2. So, and that's a times square root of 3 over 2 minus, and what's cosine of pi fourths? Square root of 2 over 2. And sine of pi 6? 1 over 2. Right. Okay. And then what would this yield us? When you multiply those two together, you get square root of 6 over 4, right? Minus square root of 2 over 4, and that would be the square root of 6 minus the square root of 2 over 4. Now, I can almost hear you saying, what difference does this make? I got a calculator, I can just plug in sine of pi 12 to get an answer. Can't I? And that's so much easier to do this, right? But this is math. It doesn't have to be easy. It needs to be fun, okay? So, but do that. On your calculator, sine of pi over 12. Be sure you're in radian mode. What answer does that give you? Going to be a small number. .258. Okay. Now, do what we just did down here. Square root of 6 minus the square root of 2. I would hit an equal sign and then divide by 4. And what do you get? Square root of 6 minus square root of 4 equal divided by 4. 0.258. So see, they are the same. And it doesn't matter which one you plug in your calculator, but that is an exact answer. These are both, and that's what they mean. When you see the question say exact answer, that means you need some radicals or pi's or something in your answer that, because you got irrational numbers. That's exact. These are approximations to the irrational numbers you have in your exact answer. Okay? Square root of 6 minus 2 over 4. All right, if I erase all that, okay? And let's see how they do it. To find the exact value of sine of pi 12, we use the fact, now they use a different one.
Uh-oh, SpaghettiOs, okay? They did the pi 6, 4 pi 12 minus 3 pi 12. That's also pi 12. I think it's going to work out the same. We hope so, okay? So let's see how they did theirs. That's going to be the formula for sine of u minus v, with u as pi thirds minus v as pi fourths. That would be sine of, you tell me, sine of, what's that formula tell you? It's going to be sine of what? Pi thirds times cosine pi fourths minus, okay, cosine of pi thirds times sine of pi fourths. Now, I started to write it the other way, and it doesn't really matter. If you wanted to keep it sine cosine, then it would be sine of this one, cosine of that. It doesn't matter. This is probably better than this other one. Do you remember what sine of pi thirds was? I've already erased it. Second? Square root of 3 over 2, exactly. Cosine of pi fourths? Square root of 2 over 2 minus cosine of pi thirds? 1/2. Good. Sine of pi fourths? Square root of 2 over 2. Perfect. And that's exactly what we had before, so it's going to come out the same. So let me go and erase my scratch here, and so you can see how they do it. Oops, they went to a new page anyway. Sine of pi thirds, cosine pi fourths minus cosine pi thirds, sine pi fourths. And when you plug in those values, just like we did, root 3 over 2 times root 2 over 2 minus 1/2 times root 2 over 2, which gives you exactly square root of 6 minus square root of 2 over 4. And it says check that on your calculator. That is 0.259, they said. And so it's sine pi 12. Okay. I sort of rounded the same. Okay, so that was example 1. Any questions on that? They skipped to example 5, so we're going to back up and do examples 2, 3, 4, if we can get them all done before we run out of time. So find the exact value of cosine of 75. Okay. How did we begin before? Wrote down all of our favorite angles, our special angles. And what are they? 30 degrees, 45 degrees. Let me write them horizontally. All right. That's how I did them before. Okay. 45 degrees, 60 degrees, 90 degrees. Okay? And somehow we need to come up with the 75 degrees out of those. Add 30 to 45, done. Okay? I think that's about the only way to. Okay? The other way we had 2 different ways. This one, that's it. So this will be the same as the cosine of 30 degrees plus 45 degrees. And what does our cosine formula tell us? Sum of the cosine of a sum formula. Say again? Cosine 30 degrees times the cosine of 45 degrees minus, because cosine is opposite sine, sine of 30 degrees, cosine, no, sine, I'm sorry, sine of 45 degrees. Wouldn't matter, they're the same, but what's cosine of 30?
square root of 3 over 2. Cosine of 45, square root of 2 over 2, minus, what's sine of 30? 1/2. Sine of 45, square root 2 over 2. And guess what? Those are the same ones we saw before, isn't it? Square root of 6 minus square root of 2 over 4. 2 times 2 is 4. So it's the same value, okay? And if you think about it, what was the first one we did? Oh, wait. Yeah. Sine of pi 12ths. Okay? How many degrees is pi 12ths? I know that takes us back to chapter 4 early on. And of course, we've forgotten. Say again? Okay. Okay. Remember, this is pi 12ths radians. We're going to multiply that by a blank blank to give you some blank degrees, right? So, in order to say again?
15.
I can't hear.
15.
It's 15 degrees. Yeah, you would do radians in the denominator. Always put the units in their place and degrees on top, right? How many degrees and how many radians, or vice versa? Remember that one? 180 degrees is pi radians. Exactly. So pi's cancel out, and this will be 12 will go into 18. 6 will go into 12 twice. 6 will go into that. 30 times 30 divided by 2 is 15. 15 degrees, right? And that was the sine of 15 degrees. And here we have the cosine of, how is 15 and 75 related? Complements of each other. And they're cofunctions. Now, of course they have the same value. You could have just said that from the beginning and we wouldn't have had to do all that work, would we? No, I'm just kidding. All right. So that just shows what we came up with makes sense. They're the same. Okay? So let's do example 3. Find the exact value of sine, now this is a little more involved problem, of u plus v, given that sine u is equal to 4 over 5. Okay? Where 0 is less than u is less than pi halves. So what does that tell you about you? Where are you living? Where did you live? It's between 0 and pi halves. Where are you? First quadrant. So everything's positive, right? Okay, so that's good to know. And they also give you something else, that cosine v is equal to negative 12/13. Now that tells you you are not, v does not live in the first quadrant, right? Because cosine in the first quadrant is positive. So v must be in one of 2 quadrants. And which ones would they be? Second? 2 or 3. Okay? This tells you, see if there's something else. This tells you that pi halves is less than v is less than pi. So where are you there? Second. Okay, so you're in the second quadrant. And the cosine is negative there. So all this is sort of making sense, right? But we want to know what sine of u plus v is. And what is sine of u plus v? Sine u cosine v plus cosine u sine v. Okay? So, we already know what sine u is. Okay? And that's 4/5. They told us that. We already know what cosine V is. What's that? Negative 12/13. But we don't know what cosine U is. Or do we? Second? Okay. All right. Now, there's several ways you can get there. I kind of like pictures myself. Okay. So I'm going to draw, U is in the first quadrant, right? Okay. It's this angle. And sine is opposite over hypotenuse. And your opposite is your y value over the hypotenuse. So I'm going to draw over here a 5 circle, right? Okay, because that's got to be my hypotenuse. 1, 2, 3, 4, 5. 1, 2, 3, 4. I can't get them all on there. 1, 2, 3, 4, 5. I'll need all those. I don't need these over here because we're in the first quadrant, right? We already determined that. So my 5 circle here would be something like that. I can go on around and blah, 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 but we don't need it. We're only here. Okay, your opposite is 4, and your hypotenuse is 5, so you're somewhere here. Okay? Now, the opposite is 4, and the hypotenuse is 5. Oh, that's the wrong place. Here's the 4, okay? Now, the question is, we need what cosine is. Cosine of that same U. This is angle U. So what do we need to know? What is cosine U? Oh, another again. Another. Adjacent over hypotenuse. Okay? Well, what's your adjacent there? How can we get it? If we know this is 4, that's 5, how can we get what that is? Pythagorean theorem. And what does that tell us? Five squared, 25 minus 4 squared, 16, 25 minus 16 is 9. Squared is, square root of 9 is 3. And it turned out, I even drew it so it looked like 3. That's why I didn't want to do this down, because I was afraid you'd trust my drawing. But indeed it's true. 3, 4, 5. Triangle, that's one of our, it's not one of our favorite ones for the trig functions, but it is a very favorite thing. It's called a Pythagorean triple, okay? 3, 4, 5. And by the way, some of these Pythagorean triples were found by very ancient cuneiform clay tablets that were way before Pythagoras' time. Now, no one has found a proof of the theorem before him, but they, people knew about these Pythagorean triples. I mean, I want to say millennia, but probably not millennia. Many centuries before Pythagoras. Okay? So, we do know what cosine U is. What is it? Second? 3/5. Okay? Oops, but we still got a problem here. We don't know what cosine V. We only knew what sine V was. But which quadrant did we say we were in? Second. Okay. But I can't use this drawing, so I'm going to erase this drawing. Well, I'm going to erase part of the drawing. I'm going, whoa! I'm not going to erase anything, am I? Okay. Yeah. I'm just going to erase parts of it here. Okay. Now, what I have to draw is what kind of circle? Not a unit, not a 5, but a 13 circle. One of my favorites, okay? Now, here's how I'm going to do that. it's not very good. Halfway there would be 6.5. So I'm going to put 6 there and 7 there, right? And halfway here would be 6.5, so I'll put 6 there and 7 there. Okay? Now, if this is 6, halfway to that is 3, and then you'd need a 1 and a 2 in between there, and a 4 and a 5 in between there. And if this was a 7, and you're going to 13, halfway in between that is a 10, so we need an 8, 9, and an 8, 9. I mean, whatever, 11 and 12 before we get to 13. Same thing up here. That was a 6, so there's a 3, so there's a 1, 2, and a 4, 5. And then this would be a 10, that'd be an 8, 9, and 11, 12. I said it right that time. So there's my 13 circle in, or quarter of it, the one that's over in the second quadrant. And cosine is what? Adjacent over hypotenuse. Adjacent is your x, so minus 12, that's out here, and there's your 13 up here. I probably don't have this one drawn quite well, but you know, it's up here somewhere, okay? I'm trying to inch that way, okay? So it's somewhere up there, okay? So if this is 12, and this is 13, right? And this is actually a minus 12, minus 12 13s. What must this be? 13 squared minus
12 squared.
Which is 144. I know that one. And then you take the square root of that. And 13 squared is 196, I'm pretty sure. So 196 minus 145 is 25. So what does that make your y? 5. You got it. I tried to sort of 1, 2, 3, 4, 5. I tried to wiggle it around to get it up to 5. So, okay. So sure enough, this is 5. Plus or minus? Plus. So that would be sine of v would be opposite over hypotenuse. There we have it, right? Now multiply those two together and you get minus 48 over, is that 165? Or is it just 65? 65, sorry. Isn't it? Yeah, 65, okay. Plus, ooh, get my pen back. Plus 15 over 65. And 15 subtracted 148 is 33 with a negative sign, negative 33 65ths. All right. So that is our sine of u plus v. Negative 3358. Does that even make sense? Well, let's see. Remember our first one there? We were up here at a degree, it was around about, I would say that was about short of 60 degrees, right? But not much. 57, something like that. This one is way over here, way past that. So if you add this to that, guess where you are? U plus v. U plus v, you would take this u value and add it to v, you're down in the third quadrant, and sine is negative in the third quadrant. I'm not sure what relative value, but at least I know you're in the right ballpark. You're in the right quadrant, right? Have you seen the softball fields? They have a field over each quadrant, so you're in the right ballpark. Okay, never mind. Okay, that was done. Okay. And they got in the book negative 33 65ths. Oh, how sad. We don't get to do example 4, I don't think. We're just right out of time. So what we're going to do is jump over to the homework exercises and do either 7 or 9. They're both, and they're 2 parts each. They're both at calcchat.com. They're not at CalcView. And then try to do any of the odds 11 through 25. They're all at CalcChat. 21's at CalcView. I think you can do any of the odds 27 through 33. They're all at CalcChat, so give them a try. And I think you can do any of the odds 35 to 39. They're all at CalcChat. 35's at CalcView. You can do any of the odds 41 to 45. They're all at CalcChat. 43's at CalcView. And you can do all of the odds, any of the odds 47 to 51. They're all at CalcChat, none at CalcView. And stop there, because we'll pick up the rest of those after we do example 4. Okay? Good deal. And there's one more assignment. Have a good spring break. And working trig will make it good, right? Yes. Okay, good deal. And in fact, I think a few of you have a test or so to work on, right? Nice time to get those. Huh? Oh, you do? Okay. Okay, no problem. I'll try to get it graded. I'll be able to grade. Okay. But I have that much grading to do, so no promises. What's that? Good deal. Okay, well, have a good one, and we'll see you in a little over a week. Tuesday week.
Oh, yeah, because of the weekend.
Well, yeah, because of the weekend, right.